Our first speaker today is Abdallah. He's from Alexandra Ross's lab, and his work is in the BioXFEL context. His work is in microfluidics, crystal sorting and such. And today he'll be presenting this time-resolved SFX paper, the most recent one, as you can see on there. So take it away, Bobby.
All right, so I'd like to thank everybody for being here today, including everybody who's tuning in. As Nadia mentioned, my name's Bobby. I work for Dr. Alexander Ross at Arizona State University. And basically a little brief background about my research. We're looking at microfluidic methods to optimize sample delivery and samples themselves for SFX. So we're looking at protein crystallization screening in microchips for efficient consumption, and also taking a bulk crystallization product and narrowing it down into different characteristics, for example, size, selectivity, and whatnot. So more importantly, though, today I'm going to be talking about the really cool paper that just came out in December in Science of the Maria Schmidt group on time-resolved SFX with photoactive yellow protein. And so as you can imagine, with these big breakthrough papers, there's a lot of authors. So like I said, it came out of the Maria Schmidt group from UWM, but also the ASU team had a big part in sample delivery, data analysis, sample characterization, and things like that, and also from a lot of collaborators around the world. So I'll first start with an outline of my talk today. So first I'll give a brief background on what crystallography is, what time-resolved crystallography is, some comparison between X-ray sources, the XFEL and the synchrotron. Then we'll look at the model system, photoactive yellow protein, experimental design parameters for this study, and some major results, basically comparing SFX data to synchrotron data, as well as some major structural findings. And I'll end with some conclusions and outlook. So I'll give you a disclaimer. I'm by no means a crystallographer, so I'm going to try to get through this as best that I can. It's going to be somewhat rudimentary for the non-experts in the room, but for the experts in the room, please bear with me. Okay, so why do we do X-ray crystallography? Well, it's one of the #1 methods for protein structure determination. Over 90% of the protein structures in the protein data bank have been solved with X-ray diffraction. And here's a brief schematic showing how X-ray crystallography works in a nutshell. So you have your X-ray source, you bombard a crystal, a protein crystal usually, with these X-rays. They scatter off the crystal into a certain pattern. These patterns are collected on a detector, and then all these diffraction patterns are basically processed with data analysis software, algorithms, and a lot of intensive work to get what's ideally the electron density map. From there, you do some refinement, and you can ideally get some kind of a protein model out of this whole process. So if we take this a step further, we can start looking at time-resolved studies, which begin to uncover the dynamics of proteins. And by dynamics, I mean how proteins are changing conformationally with some kind of an external stimulus. For example, it could be a chemical stimulus or a photoactive type stimulus, which is going to be the case for PYP. And so the nice thing about these studies is it's a 2-for-1 deal. You're getting diffraction patterns of the molecule itself, of the protein itself, and that structure, and you're also learning about the different conformations like I mentioned. When you piece those together, you can start to look at molecular movies of how the proteins actually work throughout some kind of a cycle. This is generally done with a pump probe methodology, and I show a really basic animation of how this works. So in the case of PYP, you have your pump laser, which hits your crystal. You excite it to some different state, and it begins its cycle. After you wait a certain delay, or a time delay, delta t, you then will hit the crystal at its intermediate conformation with an X-ray laser, and ideally get a diffraction pattern of that conformation. So traditionally, this is done with Lally and a synchrotron. And the reason why is because you can collect the data a lot faster using this method. Lally is basically a polychromatic X-ray source coming in and hitting your crystal. So this is a Bragg's equation, basically showing what needs to be true for you to get a diffraction spot. So in this case, you're varying lambda, which is your wavelength, and you're keeping your theta, which is the crystal orientation constant. So in monochromatic studies, you generally would rotate your crystal and you would vary theta while keeping your lambda constant. So in this case, you can get diffraction or Bragg spots in your case. The one thing that's bad about synchrotron is that you're limited to about 100 picoseconds of your time resolution. And so if you want to look at fast intermediates that happen on time scale shorter than that, you need a new method to do this. And that's what's being proposed here with the XFEL. You can actually look at these really fast intermediates that are happening. So this is just a comparison of X-ray sources. We've all seen these diagrams, but I'll briefly cover what's going on. So we have our XFEL, which is the new technology, and the synchrotron, which is still really powerful, but the last generation of technology. This is just a schematic showing what a synchrotron looks like in general. You have the storage ring where your X-rays are being generated. The process of generating X-rays is similar in that you run it through some undulators. And in this synchrotron configuration, you basically have this circular ring, and on the sides coming off of it are all your beam lines. With the XFEL, it's a linear accelerator, so it's coming through a line act. The beam itself is focused down through some mirrors and lenses, and ideally you have some type of beam line where you can add your crystals. So as we know, you have your liquid jet, which is generally the GDPM, gas dynamic virtual nozzle, coming in with a stream of crystals in solution. They interact with the laser, and ideally if you get a crystal with a beam line, then you'll see a diffraction. So this is a serial method, as we know. So you're adding a lot of different crystals to your data sets. So here's a comparison of XFEL versus synchrotron with some benefits and disadvantages for time-resolved studies. So the brilliance of the XFEL is a lot higher than the synchrotron, which allows you to get significant diffraction from smaller crystals, for example, nano and microcrystals. It goes on to say also you can, one of the benefits of the XFEL in terms of allowing you to look at smaller crystals is that you're only putting the crystal on the order of tens of femtoseconds. So you outrun the damage processes. Whereas with the synchrotron, you're exposing the crystal for a longer duration, so you need a much larger crystal. This can be problematic with time-resolved studies because with larger crystals, your excitation efficiency from your pump laser is a lot lower, about 10 to 15%. Whereas with the XFEL and the smaller crystals, you can excite a lot more of the molecules within the crystal and get more of them in the intermediate state. Another advantage of the XFEL is that we can look at femtosecond reactions, which I kind of mentioned before. With the synchrotron, you're limited to about 100 picoseconds. But if you have a femtosecond pump laser coupled with your femtosecond XFEL, you can look at intermediates that are happening on the order of hundreds of femtoseconds, for example. The other thing is because this is a serial method, you can look at both reversible and irreversible reactions. You're constantly replenishing your crystal, and you're always getting a new crystal in the ground state. And so basically, you can look at chemical reactions that are happening and not going back to the ground state after a certain period of time. For the synchrotron, you're using generally one crystal or a few crystals. And so once you excite your one crystal, if it's irreversible, it's going to be stuck in that state. Then you have to replenish the crystal and figure out if you need to do this. So that's one other benefit. Now, crystal mosaicity, again, because this is a serial method, it's less sensitive to mosaicity. However, if you have one crystal in your synchrotron that's embedded, you'll see a lot more of an effect on your diffraction. Also, with the Wiley method specifically, this can become an issue with streaking. A couple of advantages of the synchrotron, that the beam itself is very stable. So the XFEL beam, relatively unstable. The data acquisition becomes a little bit inconsistent because the laser is varying, also because you're using different crystals, different orientations and sizes and whatnot. So you need a lot more diffraction patterns for an XFEL to get high resolution data. And once again, because of this variable beam, the diffraction intensities themselves are also going to be varied. So to talk about the model system that was used in this study, photoactive protein, it's a really nice proof of principle protein to use for time-resolved studies because it's been well characterized using synchrotron data, all the way to sub-angstrom resolution. I think about 0.8 angstroms is what I found in the PDB. Basically, the function of this protein is it's a blue light receptor for phototaxis in certain bacteria. So these bacteria get hit with this wavelength of light, and it tells them which directions to move. And this is the generic structure of PYP shown in the bottom line. So as I mentioned, this is a nice protein for time-resolved studies because it has a nice photocycle. This photocycle is relatively well characterized as well. So you can see here you start with the ground state PG, and as soon as you excite it with your pump laser, you go to PG star, which is your excited state. This is a really fast intermediate, less than 100 picoseconds, that hasn't really been well characterized because the synchrotron was limited to 100 picoseconds. So this is something that could potentially be looked at femtosecond resolutions, time resolutions. You then go into the next state, which is IT. From there, you can actually have a branching off into several different intermediates simultaneously. You can have the ICT state or the PR1 state. PR1 and PR2 can then be occupied simultaneously in a mixture, and then they go down to a PB1 state. PB1 can either go back to the ground or hit another intermediate process. But the remainder of these intermediates have been already characterized because you can see their lifetimes are well beyond 100 picoseconds, so the nanosecond, microsecond time resolutions. So in terms of actually crystallizing this protein for the study, 3 methods were employed. There was a batch method, where you basically mix the 2 of the precipitants and PYP together. The precipitant in this case was sodium malonate, which the reference the structure is shown in the bottom right. You start with these concentrations, and you basically add your precipitant to a final concentration. The last 2 were modified batch methods, known as centrifugation concentration, and basically a series of centrifugation steps, spinning down steps, removal of supernatant, and so on, allows you to concentrate your protein extensively, as well as the precipitant, to get really, really large concentrations and high densities of crystals. So these were used to basically obtain a representative image shown in the bottom left of what some PYP crystals could look like. And the majority of the crystals in this study were on the nano and low micron scale, from about a few hundred nanometers up to maybe a few microns. So the experimental design in terms of the actual SFX experiment is shown here in this cool cartoon that I found. Basically, this is obviously an over-exaggeration, but it gives you an idea of what's happening. On the top left, you can actually see the pump probe scheme. So basically, you have your laser pulse, and then you have a small delay. So they use 2 time delays, 10 nanoseconds and 1 microsecond, to get the respective intermediates. After that delay, you would then have your pump. Sorry, after the delay, you would have their XFEL come in with the diffraction. Because there is only 2 28 hertz nanosecond lasers deployed, you have actually twice as much dark data as light data, because the XFEL is running at 120 hertz. So it's about 3-fold difference in between those 2. So basically, you have a light, dark, XFEL, light, dark, and so on and so forth. So this is shown in the schematic as this blue laser coming in. After this delay, then you have your XFEL coming in, and you also have your PYP crystals being fed in from the GPM. Ideally, relatively simultaneously from a macroscopic output, these are happening almost simultaneously. And obviously, you don't see the protein itself that large, because otherwise you wouldn't need X-ray soup. Okay. So here's an exemplary diffraction pattern obtained from this experiment. You can see there's spots going or extending past 2 angstroms. 1.6 angstroms to be exact, so it's very, very high resolution, which makes this the first of its kind. So basically, here's some brief statistics about the types of patterns that were actually collected and indexed. So for the 1 microsecond data, we got about an 18% hit rate. Total from that, we have about 65,000 indexed dark patterns and about half as many light patterns because of the pump probe laser scheme I talked about. The 10 nanosecond data, there's about a 5% hit rate, 45,000 dark patterns, and once again, about half the dark patterns. So of the total hits, there was about a 65% indexing rate, meaning 65% of the patterns were indexable. So from these patterns, different electron density maps were then constructed. And that's basically the light structure minus the dark structure in a nutshell. Now it's very much more complex than that. For the purpose of this, hopefully that suffices. So before I go on, I kind of put this cheesy stereo tutorial up. You guys might know how to do this because all the images in this paper were in stereo, and I know usually you put this into software to be able to look at these images in 3D, but you can actually also do this with your own eyes. And so basically you can follow these instructions if you'd like to attempt it, or maybe you already know how to attempt it. You can view these images in 3D if you're really good at focusing eyes. So you basically cross your eyes and look at the left image with your right eye and the right image with your left eye. You can kind of guide this by sticking your finger out in front of you, focusing on your finger to cross your eyes, and then ideally defocusing and trying to focus on the blurred image that shows up in the images. So it's really hard to do this, but if you're able to, it's totally worth it, because you can get a 3D picture out of a 2D image. So the first set of data that I'm going to talk about is a DED map from the 1 microsecond delay point. And basically the red portions are negative density, and the blue portions are positive electrons. In the background is the dark structure, shown in cyan/yellow. That's just for reference. You can see that there's a really large feature around the chromophore, because when this PYP molecule is absorbing light, the chromophore is obviously where the maximum absorption is happening. So there's a huge dip, a huge change. So what's happening is actually an isomerization. There's a double bond, carbon-carbon double bond in this chromophore that's actually going from a cis to trans isomerization event. So it's a pretty big deal, a pretty big change happening. But it's also important to note that there's actually some DED features extending all the way to the periphery of this protein. So there's actually structural changes happening all the way out. However, the largest is happening where this sulfur portion is actually displacing the chromophore. And the bottom image is simply a 90-degree rotation of the top image. And for reference, at the 1 microsecond time point, this is just showing the photocycle in terms of the relative occupancies of the intermediates. You can see that you get the PR1 and PR2 occupants at this time point. So for a comparison to show the importance of why high-resolution data is needed for these small, tiny structural changes in these intermediates, we can look at lower resolution data. Basically, these are also DED maps at 3 angstroms and 5 angstroms. And you can see even at 3 angstroms that there's a huge loss of DED features even at that resolution show. So the chromophore region is within here where you see PPA. You can see a lot of DED features are lost. And then at 5 angstroms, you basically lose all the features. So it's really important to have this high resolution 1.6 angstrom data to begin to see these really tiny changes in these displacements of the amino acids and the chromophore itself. One thing to note, though, is that these are by no means absolute measurements, so 3 angstrom and 5 angstrom wouldn't necessarily be true for another protein in another system. This just happened to be the case for this experiment. So for other types of experiments, you want to look and see what kind of resolution you actually need to uncover your features. But I think everybody ideally generally goes for the highest resolution they can possibly obtain. So if we look at a little bit more of a close-up of this chromophore pocket, and also additionally the 10 nanosecond intermediate data, you can see on the bottom left, this is the dark structure from SFX. And I highlighted the blue 46 amino acid because it shows a significant displacement overall. It plays a big role in this isomerization. So this chromophore is actually put together by hydrogen bonding. There's a lot of changes that go on with this bonding that happens. And the blue 46 is predicted to have a big part of this. So once again, on the top left, I'm just showing you for reference the photocycle. And above each of these images shows the main intermediate that's present at this time. So in the case of the 10 nanosecond data, you can actually see that there's really 3 intermediates being populated. And there's a lot of changes in these intermediate concentrations at that point. So it's hard to really resolve each individually. But in this case, in B, it's basically showing the ICT intermediates refined in the background just for reference. And you can begin to see some feature changes or some DED features showing up within the chromophore already. And also you can see this displacement of this blue 46. Once we go into the 1 microsecond data, however, there's a really significant change in this chromophore. And that's really because the PR1 and the PR2 states are significantly occupied at that point. And they have a really long lifetime. So you can get really good features out of this. And also there was more data collected for 1 microsecond points. And so in this case, for the So this is basically a stereo image of what I just showed, but there's some other interesting things to point out here. So from this SFX data, there's actually some DED features that are unknown. So there's some unknown structural changes that were uncovered and probably need further studies to uncover. But it just indicates that there's still a lot to learn about these intermediates, and potentially there are more intermediates to be found. So once again, the yellow is the dark state, and then we have our intermediates shown in various colors. Another thing that's interesting that I mentioned before is that the DED feature strength between the two, you can really emphasize now that there's a lot more DED features happening in 1 microsecond versus 10 nanoseconds. And like I said, also there's about 3 intermediates happening at 10 nanoseconds. So these arrows for alpha, beta, and gamma are pointing to DED features that would correspond to other intermediates that are difficult to separate out because they're changing so fast. So if we look at a refined 1 microsecond intermediate structure, these are actually both the PR1 and PR2 in the same image, and this is again a stereo image. We can begin to calculate the amount, or the percent occupancy of each intermediate in.
Can you use the mouse instead of the pointer? Because I can't see it.
Yeah. So, we can begin to calculate the percent occupancies of both the PR1 and PR2 based on calculated and observed DED features in both. And so in this case, they were able to calculate that the PR2 is about 55% occupancy, and PR1 is at about 45% occupancy. And overall, the reaction efficiency was about 40%. So like I mentioned at the beginning, a lot higher than what was done with synchrotron, which was around 10 to 15%. We would expect there to be about a 60-40 split between these two intermediates. So basically, this is in relatively good agreement with the concentrations we would expect of them. So now the kicker is basically comparing the XFEL data to the Lowry synchrotron data. And this is one of the major points to bring up because it shows that SFX can actually be better than synchrotron at doing time-resolved studies. And so on the top is basically the image I showed before for SFX, the dark structure, the 10 nanosecond to 1 microsecond. On the bottom, though, is a comparison with the synchrotron Lowry data that had been obtained previously. And so the dark structures themselves look very similar. They can be refined similarly, so very good agreement there. Lowry was done at 32 nanoseconds, but relatively the same intermediates were seen in both cases, so it's a very good comparison between the 10 and the 32 nanosecond time points. And then on the far right, you see the 1 microsecond intermediates. The one main thing to notice, though, is that the DED features in the SFX data are much more pronounced than that in the synchrotron data. And this has to go back to the fact that the crystal size was much smaller. In the Lowry data, you're looking at maybe 20, 30 to 100 micron crystals, where in this case, we're looking at maybe a micron precise crystal or a nanocrystal. So the reaction efficiency is a lot higher, and so you can really uncover more of these intermediate changes because there's more molecules in the intermediate state overall. So this is a really big selling point for SFX, in that now we can actually start to really see what's changing at these fast intermediates and intermediates where there's really, really small changes happening. So to conclude, this paper really demonstrates that time-resolved SFX at an XFEL is possible. So you can do it at high resolution. You can also study really ultra-fast reactions, less than 100 picoseconds that we were limited to before with the synchrotron. You can see the really short-lived intermediates that are less than picoseconds. The other thing that was mentioned is that you really need high resolution to see some of the small feature changes. So we extended out to 3 and 5 angstroms, and you really lost a lot of the DED features that you found in the 1.6 angstrom structure. So that's important to really begin to uncover new intermediates and things of that nature. Additionally, at the end, we compared with Lowry data, Lowry from synchrotron, and noticed that the DED features overall at the XFEL are a lot higher because your reaction excitation efficiency is a lot higher at the XFEL. So you can uncover a lot more information about the chromophore overall. And hopefully with further studies, you can begin to learn about cool absorption phenomena, how chromophores work in general. This could be translated over to photosynthesis, sensing, vision, and all kinds of really interesting applications. So it's a really important field. So that, I'd like to thank everyone for their attention.
Thank you, Bobby. Do we have any questions?
Do we have any questions?
Hi, this is Ed Latman.
Yes.
You mentioned that the proportions that you saw in the two photo states were as expected. Does expected mean the results of spectroscopy experiments? What was the other measure of the populations of those two states you were comparing to?
In a nutshell, yes. So the literature that I found were done with spectroscopy, and basically they were just looking at different absorption phenomena to get an idea of what type of percentage concentrations each were in. So that's my comparison.
Thank you.
Any more questions?
What do you expect to see, I'm sorry if you said this, on the nanosecond scale that we couldn't see here? What do you expect to see?
You mean on the sub-picosecond? Or?
Right, sub-picoseconds. My bad.
So we would hope to see the PG star, so the initial excited state of PYP, in this case.
Is there any delay in PYP starting to change into the next state? I mean, are you more likely to have these get activated, they start changing, then these, then these? Do you think you'll start getting more of a mess if you go to shorter and shorter times?
Mm-hmm.
Or do you think there's more of a mess when they decay?
I would say probably the decay is more of a mess overall. One thing to note actually is when it splits off into PR2 and PR1, the lifetimes of each are actually quite different. And so the overall photocycle can actually change separately for different pathways. That's also one issue that could arise.
Does anyone else have any questions from across America? Okay, good. All right. Thank you, Bobby.
Thank you.